You are 53 years old. You are standing in a corridor outside a hospital room. A doctor is telling you that your heart is failing. Not slowly, not eventually. Now. You have months, maybe less. There is a donor list. There are thousands of names ahead of yours. The doctor is kind. The doctor is honest. The doctor tells you to go home and wait. In 2085, that conversation will not exist. Not because hearts stop failing. They will still fail. Not because medicine becomes perfect. It will not. But because by 2085, the solution to a failing heart will not come from a stranger's chest cavity. It will come from a printer. It will be built from your own cells. It will be yours before it beats its first beat. How did we get there? To understand where bioprinting is going, you need to understand what a heart actually is. Strip away the mythology, the Valentine's Day symbol, the seat of emotion, the thing poets have written about for 3,000 years, and what remains is a pump. A four-chambered muscular pump, roughly the size of your fist, beating 100,000 times a day, every day, for your entire life. It does not ask for rest. It does not take days off. And when it fails, nothing else in your body works either. For most of human history, when a heart failed, the person died. Full stop. Then in 1967, Christian Barnard performed the first successful human heart transplant in Cape Town, South Africa. The patient lived 18 days. The world called it a miracle. And it was. But it also revealed the central problem that would haunt transplant medicine for the next 60 years. The body does not want someone else's heart. The immune system treats a donor organ as an invader. It attacks it. Without powerful immunosuppressant drugs taken every single day for the rest of a patient's life, the body will destroy the very organ that is keeping it alive. That problem has never been fully solved. Today, roughly 3,500 heart transplants are performed in the United States each year. The waiting list holds over 100,000 names. Globally, the gap between need and supply is even wider. Hearts cannot be stored. They must be transplanted within hours of removal. Every year, people die waiting. Not because the surgery is impossible, because the organ does not exist. Bioprinting is the answer to that scarcity, and it is already being built. Here is the neo. In 2019, researchers at Tel Aviv University produced the first 3D printed heart using human biological material. It was small, roughly the size of a rabbit's heart, and it could not yet pump blood effectively. But it was made from human cells and human biomaterial derived from a patient's own fatty tissue. It was, structurally, a heart. Professor Tal Vavier, who led the research, called it a proof of concept. The scientific community called it a turning point. That same year, a separate team at Carnegie Mellon University developed a technique called FRESH, free-form reversible embedding of suspended hydrogels, that allowed soft biological materials to be printed with precision previously thought impossible. The technique was used to print a full-scale model of a human heart, including the internal chambers and major vessels, using cardiac cells derived from human stem cells. The work was published in Science. It was not a functioning heart, but it was the right shape, the right scale, and the right material. The architecture was there. Meanwhile, at Wake Forest Institute for Regenerative Medicine, a team led by Anthony Attala has been printing functional human tissue for over a decade. Skin, cartilage, bladders. Some of these printed tissues have already been implanted in human patients. The bladders work, the cartilage integrates. The body accepts them because they are built from the patient's own cells. No immunosuppression required. That is the key. That is everything. Now project it forward to 2085. The process begins before you feel any symptoms. Sometime in your 40s, as part of a routine health scan, a sample of your cells is taken and stored. Not because anything is wrong, because this is now standard practice, the way blood type was recorded in the 20th century. Your cellular blueprint is archived. When your heart begins to fail, flagged 2 years in advance by an AI monitoring your biomarker data, the process is already in motion. Your stored cells are retrieved. They are reprogrammed into pluripotent stem cells, meaning they can become any tissue in your body. They are then differentiated into cardiomyocytes, the specific muscle cells that make up the heart wall. This process, which took months in the early trials of the 2020s, takes days. The printing begins. A bioprinter, a device that by 2085 looks nothing like the clunky laboratory machines of the early 21st century, deposits layers of living cells in precise three-dimensional patterns, suspended in a hydrogel scaffold that holds them in place while they organize and mature. The scaffold dissolves. What remains is living tissue. Layer by layer, chamber by chamber, valve by valve, your new heart takes shape. It takes approximately 72 hours to print, another 2 weeks to mature in a bioreactor, a controlled environment that keeps the tissue alive and gradually trains it to contract rhythmically, the way a heart must. By the time it reaches the operating theater, it has already been beating for days. The surgery itself, by 2085, is performed by an autonomous robotic system with real-time intraoperative imaging. The procedure takes 4 hours. You spend 3 days in recovery. You go home. You take no immunosuppressant drugs. Your body does not reject the heart because the heart was never a stranger. It was always yours. Here is the counterintuitive twist. The end of the donor heart shortage will not end the ethical crisis around transplantation. It will create a new one. If a heart can be printed from your cells, what about a brain? Researchers at Johns Hopkins and the Allen Institute for Brain Science are already growing brain organoids, simplified miniature versions of human brain tissue, from stem cells in laboratory dishes. These organoids exhibit electrical activity. Some have developed rudimentary sensory responses. Nobody yet knows exactly where the line is between a cluster of neurons in a dish and something that experiences. But the line is coming into view. By 2085, the question will not be whether we can grow organs. We will be able to grow almost any organ. The question will be which organs we are allowed to grow, and who decides. In a world where a heart is printed from your own cells in 72 hours, the concept of mortality changes, not disappears. Changes. The failures that kill us will shift. Hearts will be replaced. Livers will be replaced. Kidneys will be replaced. The organs that currently end lives prematurely will become gradually renewable. What remains unreplaceable, which, for now, is the brain itself, the seat of memory, personality, consciousness. The one organ that cannot be swapped out because swapping it out would mean becoming someone else entirely. That is the new frontier. That is where the next battle will be fought. For the first surgeons who transplanted a donor heart 60 years ago, the act was extraordinary. It required a dead stranger, a living patient, a race against time, and a lifetime of medication just to stay alive. It was heroic precisely because it was so difficult. You are 53 years old. You are standing in a corridor. A doctor is telling you that your heart is failing. In 2085, the doctor does not tell you to go home and wait. The doctor tells you to come back in 3 weeks. Your heart is already being printed. So the question for you is this: if the organs that define your biological life can be replaced one by one, at what point does the body you were born with stop being yours?